Okay, let's get started. We're going to continue on in chapter two. Excuse me. And today we're going to be describing sets. It's going to be a whole lot of vocabulary and terms, a little bit of problems, but mostly just really kind of understanding here. Okay, so in the late 1800s, the mathematician George Cantor changed mathematics forever, like in a way that hadn't really been changed before. And there had been lots of big discoveries coming up to the 1800s. But Cantor brought to the world something called set theory. And of course, this happened like in many famous mathematicians that his discoveries were embraced and used after he died, so posthumously. Let's get started with the definitions. The first one is a set is a collection of objects, and each individual object in a set is called an element or a member of that set. Notation is super duper important here. And when an element belongs to a set, we use this symbol right here, and it means an element of. And we can describe sets in a bunch of different ways, but mainly two ways in this context. We can describe a set in list form by literally listing out all the members of the set, or we can use something called a set builder notation. So here I have the exact same set written in list and also written in set builder. And so I need to decipher and tell you what all that set builder business means. So here we have the set of 1, 2, 3, 4, 5, and 6. And when we make the set builder, a couple things are always consistent. We always have around curly braces, okay? So you got to have curly braces to indicate that it's a set. We have X, so we have to have a variable such that this straight line means such that. And this piece here says X is an element of the natural numbers. And we're familiar with the natural numbers. That's really all we've been working with so far. So those are the numbers that are the counting numbers. They start with 1. And this little comma, and sometimes they just write the word and X is less than 7. So there's a second condition here. The first condition is that it has to be a natural number. That tells us a couple things. It starts with 1. There is no 0. There are no fractions. There are no decimals, the counting numbers. Okay, so that's how you kind of read set builder. Let's practice a little bit with that. Now, when we're describing sets and set builder notation, you might have to lean on what we've learned in sequences. So you're going to might have to lean on the knowledge of sequences. And I want to remind you that the nth term of the arithmetic sequence is a sub n is equal to a sub 1 plus n minus 1 times d. And what makes something an arithmetic sequence is the common difference. So the first thing you should always do if you're needing to come up with a formula that describes the behavior of a set is to see if it is an arithmetic sequence. And in fact, all three of these are arithmetic sequences. All right, so let's take a look at the first one here. Now, you might be able to tell me in words. So let's just write out in words what's happening here. Looks like this is all the even numbers, right? Looks like it's all the even numbers. And another thing that we want to kind of pull together here with sequences is we're going to consider these like a sequence. So this is term one, this is term two, this is term three, this is term four. It doesn't really matter what the value is, that's what term it is in the set. Okay. And we're trying to build a pattern here. So these are even numbers. So let's just utilize what we know here. So the first thing we want to know is what is D? And D here is 2, right? Positive 2 to get to the one to the next, we added 2 to get to the next one, we added 2. So our common difference is 2. We also need to know what the first term is, right? That's that A sub 1 in this notation over here. And that first term here is 2. And then we can just use the formula. So I'm going to say A sub n is equal to 2 plus n minus 1 times D. And then we can clean that up. So 2 plus 2n minus 2. So A sub n is equal to 2n. So this is the sequence that gives the elements of the set. Okay, that's why this chapter started off with sequences. Okay, so we can be able to do this. So let's get that set builder. So the set builder will be X such that X is equal to 2n, where n is an element of the natural numbers. Okay, and I'm going to write that out in words so you know what this means, because it'll take a little bit for you to be able to read what that means. So I'm going to write out explicitly the words here, and it's going to be X such that, oops, I forgot my H in my that. Sorry about this. X such that X is equal to 2n and n is an element. I cannot spell today at all. Holy crap. Yeah. An element of the natural numbers. And yes, you need all of that, okay? Because you're describing the set. All right, cool. So let's look at this next one here in words. And you don't have to do this. I just want to do this so you can kind of see how you can reason this through, how you might be able to baby step a student into this, right? So in words, these are the odd numbers. Again, the common difference here is 2. The first term is 1. So let's do it. A sub n is equal to 1 plus n minus 1 times 2. So that's 1 plus 2n minus 2. So we get 2n minus 1. This is the sequence that will give you odd numbers. It just always does. Okay, and so we'll put this guy in set builder. This is going to be x such that x is equal to 2n minus 1, where n is an element of the natural numbers. All right, cool. Well, let's do this one as a you do. So let's pause the video for a moment. Take yourself about 2 or 3 minutes and get this going, and I will be back in just a minute. Okay, how you doing? Now, we can't really say in words here other than we can say what the common difference is. We can say that it's arithmetic. We can say there's a common difference because it is a common difference of 3. So let's just get it going. Again, if you have not finished, please just pause the video and finish and then start back up so you can check yourself. All right, so here D is equal to 3, A sub 1 is equal to 1, so we're going to say A sub n is equal to 1 plus n minus 1 times 3. It's 1 plus 3n minus 3. It's going to give us negative 2, oops, y, hello, 3n minus 2. That is going to be the sequence that's going to give us all the elements of the set. And our set notation is going to be x such that x is equal to 3n minus 2, where n is an element, not of the integers, sorry about that, it slipped into one of my other classes, of the natural numbers. All right. Cool. Okay, so this is how to describe the sets in set builder notation, and I certainly did the harder part first. Let's list out some set terms here. So looking here, it says describe the following sets and list terms. Now notice on this first one, it said x such that x is equal to 2k plus 1. And specifically, k is equal to 3, 4, and 5. That means, number one, there are only 3 elements of this set. So just note 3 elements. Okay? That's what we've got going on there. So we can say C is equal to, in the curly brace, and we're just going to plug in the 3, plug in the 4, plug in the 5, and get those 3 elements. So when we plug in 3 here, we have 2 times 3 plus 1 is equal to 7. Plugging in the 4, 2 times 4 plus 1 is equal to 9. And plugging in the 5, 2 times 5 plus 1 is equal to 11. And there is our explicit list. The next one is basically the same, but no real math involved here. We're going to say D is equal to, and it's x such that x is even and under 12. Now, I should have said also, and x is an element of the natural numbers, because I didn't explicitly say we're dealing with the natural numbers here, and it should have said that, okay, to be precise. And so here we go. It's even. It's a natural number, so the first natural number is 2, 4, 6, 8, 10, and it says and under 12. So that is our set. Not to include 12, just under 12. Could have said under and including. It could have said x is less than or equal to 12. But what this actually says here is x is less than 12. Words matter. And will be pointed out. Okay. All right, sorry about that. Okay, let's keep on going. More definitions. Yes. So two sets are equal if and only if they have the exact elements, the exact same elements. So it could be 1, 2, 3, 2, 1, 3, 3, 2, 1. Those three sets would be equal because they contain the same elements, order not mattering. Another big concept here is something called one-to-one correspondence. And one-to-one correspondence happens when your two sets are the same size, right? And each element in the first set could be mapped to a unique element in the second set. And we'll think of something like this. I'll draw a little visual here. So if we had something like 1, 2, 3, 4, and we have A, B, C, D. Now, this describes a one-to-one correspondence because each element in the first set could be directly mapped to an element in the second set. And that shows one-to-one correspondence. But if we have, say, this 1, 2, 3, and this A, B, C, D, and E, this does not have one-to-one correspondence because there's things left there. Okay, so this is not one to one, and this is one to one. Okay, all right. So I just want to make sure you understand that. So let's consider a situation here. We're at a meeting and you get to choose one appetizer and one entree from the menu, okay? And the question is, if we have two entrees, I mean two appetizers, soup and salad, and three entrees, burgers, gyros and calzones, then how many different meals could we actually make up of that? Like how many unique meals would we make from that? And what I'm going to do is I'm going to use a tool called a tree diagram to demonstrate here. So here is my tree diagram. And everyone can, do it the way that they want to. But basically, we start off with the first two choices. We have salad and we have soup. And if you chose the salad, you then have three choices. And if you chose the soup, you also have the three choices. And so I don't have to write all these down. I'm going to use these letters, right? So we got burger, gyro, calzone, burger, gyro, calzone. Now, the cool thing about the tree diagram is the last branch of the tree diagram indicates the total number of choices. Boy, I cannot write today. Okay. So how many meals will we make? 1, 2, 3, 4, 5, 6. There are 6 meals. All right. Makes sense. Now, a little caveat I have to say here. This particular technique only works when what we're pulling from is unlimited. Okay, so we're pretending like there's an unlimited amount of salad, soup, burgers, gyros, and calzones. So it doesn't affect the next person's choice on what the person before has chosen. Okay, that is a very important distinction that has to be made here. Okay, now what happens if I decide to include dessert? Like, what does that do? Well, I do love me some dessert. So let's draw another tree diagram here. And this is going to be our burger, our gyro, our calzone, and then we're going to use P for pecan pie, B for banana, or BP for banana pudding, and C for chocolate cake. Okay, we'll do this. PP for pecan pie. That way it's consistent. Okay? All right. So let's get started here. So we have our first two choices. All right, we have our soup and we have our salad. And then off of those choices, we have three choices. We have our burgers, our gyros, our calzones, our burgers, our gyros, our calzones. And then off of that, we have our new choices: pecan pie, banana pudding, chocolate cake. Pecan pie, banana pudding, chocolate cake. Pecan pie, banana pudding, chocolate cake, and then again over here. Now you can see that this is a very helpful tool here because we can visualize it, we can literally count it, but what if we had much more options than the few that I have written here on this example? This could become quite the nightmare. So, can we see a pattern? Is there a way that we can describe this without actually drawing it all out, writing it all out, or anything like that? Just for funsies, let's count here: 3, 6, 9, 12, 15, 18. So, there will be 18 different meals with dessert. Now, if there were 6 meals with these two options, and now there are 18 meals with these three options, can you see a pattern emerging? In fact, there is, and this brings us to something called the fundamental counting principle, okay? And so what the fundamental counting principle says is if event M can occur in M ways, so choosing a soup or salad could occur two ways, so that would be one event. And event N, choosing your entree, could occur in N ways. In our case, it was three ways. Then the event M, choosing an appetizer, followed by the event N, choosing an entree, could happen in two times three ways. And we've already shown it. There were 6 options. Okay. Now this can be extended to an infinite number of events. And we showed that because, well, I said, what happens if we add dessert? Well, there's 6 options when there was just soup and entree, and now I've added in the 3 options for dessert, and that changed the whole thing. Now, here's what I want to ask you. What if there were only 2 dessert options? Pecan pie and banana pudding. Then in that case, then there are only going to be 12 meals, and that's literally due to just the math there. Okay? So, and the fundamental counting principle only works when choosing from a event does not change the next person's choosing from that event. In other words, it has to be done with what's called replacement, meaning that it never runs out. It is an unlimited amount. Okay, so you can only apply this fundamental counting principle in that case. Now, there's a second situation here. So, this fundamental counting principle only works if it's like unlimited. Okay, it would not work if, say, there were 20 possible. It would not work if, say, there were 20 burgers, 20 gyros, and in 20 calzones and they're feeding 60 people because as a person picks a burger, there's less burgers and there's only so many, there's a limited number. Okay. I hope I didn't belabor this too much, but I remember that this confused the absolute dog meat out of me when I was first being introduced to kind of like these set theory ideas. I just got super confused because it would work in one instance, but that wasn't the right thing to use in the other instance, and I couldn't see the detail between the two, the nuance, so to speak. Okay, so let's look about what happens when it does matter, like when there is not an unlimited amount. This is a case of not an unlimited volume to choose from. I just want you to be able to see this. So, okay. Now, here's this question. What happens when the choice is removed from the set after it's chosen, right? So it changes the way we do things. Let's look at how many different ways we can arrange these five numbers. Just literally, how can we rearrange five numbers? Okay. So the best way to think about this and to get your brain to really wrap around this is think about it in this way. This is the first choice. This would be the second choice, right? Third, fourth, and last. Okay. Now, if we have these five numbers, how many choices do we have for the first number? The first one we choose? Well, we could choose any of them, right? So the first number, we can choose five. And I'm just going to mark one randomly off. It doesn't matter. I'm just doing it for visuals. For the second choice, well, how many numbers are left? There's not five numbers left anymore. There would be five numbers if it was an unlimited, right? But this isn't an unlimited list. This is a finite list, a list of five numbers that we have to choose from, not an unlimited volume of calzones. Okay, so there's only four choices for the second number. How about the third number? There's only three choices for the third number. Two choices for the fourth number, and there's only one choice for the last number. You've exhausted what is in there, right? So this is it, and these are all multiplied together. And so the number of ways to choose the five strings is 5 times 4 times 3 times 2 times 1. So 20 times 3 is 60 times 2 is equal to 120 ways. Now, this is kind of a little special mathy thing. You may remember this from your college algebra class. I am just now teaching college algebra down here for the first time. And of course, the content is a little different, so I'm not 100% sure you saw it. So I would want to talk about it for a second. This brings us to a concept of factorial. This is a factorial. And a factorial is defined like this. N factorial is equal to n times n minus 1 times n minus 2 times dot, dot, dot times, say, 4 times 3 times 2 times 1. This indicates that it's every number from whatever n is all the way down multiplied together. So what we have up here is 5 factorial. That's not 5, yelled at you. That's 5 factorial. So if I wanted to do something like, and these numbers grow crazy huge. They don't grow quite as fast as exponentials, but they grow insano. Um, but like if I said 10 factorial, just double that number, right? That would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, you don't have to do that fully like on the calculator. There is actually a button on your calculator. I did not think about showing you any calculator things today, so I didn't pull up my online calculator, but I will give you the quickie steps here, um, just in case you don't know. But let me get that number real quick and then I'll give you the answer. That is equal to 3,628,800. So big, big growth. And the calculator steps are, first thing is you oh goodness, be glad when this lecture is over today. Enter the N. Then you're going to hit the math button. And you're going to arrow over to the probability. So that's 1, 2, that's the third arrow over to PROB. And enter, and then you're going to go down 4 to the factorial, enter. You might have to enter twice, and that'll give you your answer. Okay? All right. Let's get back to non-math, non-mathy feeling things. Okay. More set theory. So two sets, A and B, are equivalent, and the symbol is that little squiggly tilde. If and only if there exists a one-to-one correspondence between the sets. And let's remember, what does it mean to have a one-to-one correspondence? It means these sets have to be the exact same size, same number of elements, because each element in set A has to map to a unique element in set B with none left over. Okay? So that means that each elements they have to have the same number of elements. Now, don't miss the difference here between equal and equivalent. It's important. Equal means the elements are exactly the same, and it also means that they are equivalent because they're of even size. But equivalent does not say that they are the same elements. Okay, so be careful with that. Let's lean into it just a little bit. And I have us 4 sets right here, and we're going to compare the sets and determine their equal and equivalent statuses. Now, I think right off the bat, you can see that set A doesn't fit jack nothing, right? It's not equal because there are no other sets that have P, Q, R, and S in them. And it is not equivalent because that is a 4-element set and all these others are 3-element sets. So first thing I'm going to say is I'm going to say A is not equivalent to B. A is not equivalent to C, and A is not equivalent to D. I can say that straight up. Right, now what else can we say? We can also say A is not equal to B, A is not equal to C, A is not equal to D. And this might seem redundant, but it is really important that you can list out all of these things. This is important. Now, we've we've managed all this business with A. Let's turn our attentions back here to the B, C, and D. Now, we can easily say that B is equivalent to C, B is equivalent to D, and C is equivalent to D because they are all three elements, right? That's all that matters. Same number of elements. Now, what else could we say? We could say that B is not equal to C, but B is, I don't know why I went to a lowercase b there, my bad. But probably because I said but, I shouldn't have even said but. I should have just made a comma. I mean, I wouldn't mark you off, but comma, and then we can say B is equal to D. And that's pretty much all we can say about the equivalency statuses. And it's probably more than you would have wanted to say, right? Like I went on and on, but we want to be very explicit about the relationships between these three sets. Now, equivalence brings on another very important concept, and it's the concept of cardinal numbers. Okay. And the cardinal number is just a way to say how many elements are in a set. Okay. And it's denoted by, let's see, like n of set A is equal to 3. That would be the cardinal number of A. All right. And so I've gotten in our example here 3 different sets, and they have wildly different elements. We've got letters, numbers, and symbols, but these guys would be equivalent sets because they have the same number of elements. And what we say more sophisticatedly is that they have the same cardinal number. So the cardinal numbers are the same for sets A, B, and C here. And that way we can say that they are equivalent. So I didn't even write that here, but I could say, therefore, equivalent. Okay. Now, a set that contains no elements is called the empty set, right? And I think we might have talked about it. Maybe we're just now talking about it. But the empty set is denoted with a circle with a slash or an empty set of curly braces. Either one of these mean an empty set. Now, the thing to be noted here, the thing that is kind of hard to wrap your brain around is that the cardinal number for an empty set is 1. Okay? Because it can be, well, it's really not a cardinal number. I'm sorry, I misspoke. We have to say that an empty set is finite because we can count the fact that there is nothing in it. Okay, so there's 2 kinds of sets. There's the finite set, a set where we can literally count and say exactly how many elements are in it. And then we have the infinite set, like the set of natural numbers. We can't count them. We can't list them all out in a list. Even if we had all of our lifetimes strung together to continue to just write out these numbers, we would never get to the end, right? So that means that that's infinite. And what I guess I need to make sure you understand is that if it is an empty set, it is not infinitely empty. It is countably, not a real word, but I think you understand what I'm saying, countable as 0. And since it can be counted as nothing, then it is finite. Okay. If the set cannot be counted, it is an infinite set. So here's an example here. Let's just determine whether this is an infinite or finite set. The first is a set of even natural numbers. And even though there's some qualifiers there, I'm not saying all natural numbers, I said even natural numbers, we know that that is an infinite set because we could not write them all down. So this is infinite. And the next one is x such that x is equal to 2k minus 1, k is less than 7. So that's a finite set. And indeed, that's a finite set of odd numbers between 1 and 7, if we want to look at that more closely, right? Okay, cool. We're going to move away from this. Now I know this is a lot of information. This is tons and tons of information, and I understand that. And it doesn't seem like it all kind of like goes along a path. It seems like maybe I'm like, and let's do this now, and let's do that now. But it will all kind of meld together, and then we'll put it all together with some more math when we get to the last section of this chapter, which is 2-3, the next lecture. Okay, so just bear with me. We got to get all these fundamentals down so you can understand the problems. All right, the universal set. Okay, the universal set is the set that contains all the elements being considered, and it is denoted by a U. Okay, we can't consider every single possible number, right? Because with it, if we do that, we're including fractions, decimals, irrationals, pi, e, all sorts of numbers. So often when you're dealing with sets, there is going to be some sort of a universal set that we're dealing with inside of. That's the way to kind of manage it a little bit, okay? And so we're going to kind of like deal with that idea. Set A is a set of even natural numbers less than 100. Okay, so we've got A is equal to X such that X is an element of the natural numbers and X is less than 100. Notice I didn't say less than or equal to. It is straight up less than. Be very mindful when you read. Okay, it's all about real critical reading. And a lot of times when students are in math, and this starts early, this starts super early in elementary school, they don't think the words are important unless it's a word problem. They don't think the words are important, but the words are very, very important. And critical reading is super important in mathematics. Okay, so I wrote this out and I say, what could the universal set be? And note I said that this is not a unique answer. The universal set could be a multitude of things, right? I could say, did I write the same thing down over here? I did. This is the same example. I don't know why I wrote two examples there when it was all in the same example, but I did. Okay, hi. All right. So if it's the set of even natural numbers less than 100, oh, I did, that's what's wrong. I didn't write this at all right. Let's fix that. Let's fix that before you think that I have not fallen down and hit my head. X is equal to 2n. This part makes it an even number. Has to be a different variable because remember, now we're going to be counting through to get those different elements. Remember that the set is kind of like a sequence. Okay, so X such that X is equal to 2n. X is less than 100 and n is an element of the natural numbers. Okay, so we got to know when to start. All right. Plus, it already said it was a natural number, so I explicitly put it here. Okay. So here's one of them that I wrote up. I was like, hey, you could be an element of the natural numbers where x is less than or equal to 100, right? And what would that set look like if we kind of listed it out? It would be something like 1, 2, 3, dot, 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 99, and 100. Now, would all the even numbers less than 100 fit into this set? Absolutely. So there's one. Let's think of three more. So let's think of three more. And if we were in the classroom, I would have you holler them out to me. But since we're not, and there's the obvious ones. We could say X such that X is an element of the natural numbers and just leave it at that. It's all the natural numbers. Okay. That is an infinite set, though, not finite. This is an infinite set, not finite. This one here is a finite set. All right. And often it behooves you to come up with a finite set. So there's one of them. What? It's an okay one. It's just an infinite set. What's another one? X such that X is what? What else could it be? It could be an element of the whole numbers. We haven't really talked about that very much, but the whole numbers, I know I've mentioned, start at 0. And that's the only difference there. Oh, my bad curly brace right there. 0, 1, 2, 3. All right. I'm sorry I said three more. Let's think of another one that we could do. I really should have thought of three, so I would have had them ready. Let me just flip the page and see if maybe I came up with one. Uh, Not really. I guess we could write it something like this, X such that another one I wrote down is something like this, that we could do it like this, kind of weirdly. Um, we could do something like that. X such that X is between 1 and 100 because it's an even number. So it would, 2 would fall in there and 98 would fall in there. So, I mean, that would work too. Okay. I'm done with this one. All right. Let's keep on moving. Okay. So the universal set was discussed to set up the idea of the complement of a set. So consider what's not in set A, but is in the universal set. There's a name for those remaining elements, and it's called the complement of A, and there's actually a notation for it. It is the set name with a bar across the top of it. So looking here at our example here, I said, what is the complement of set A? If A is the set of even natural numbers less than 100, and the universal set is all the natural numbers greater than or equal to 100. Now, it does not hurt at all for you to kind of like list out some of these guys, right? So this is going to be 2, 4, 6, going up to 96 and 98, right? There's no 99, no 100, because that's a set of even numbers, even natural numbers. And it's helpful to write these out. If we look at this, our universal set is the set of all natural numbers where x is less than 100. So 1, 2, 3, 99 less than or equal to 100. So that is what our universal set looks like. So what would our complement look like? Well, it looks like it's going to be all the odd numbers, right? Whatever's not in A is going to be left in A complement. So one, three. Do you think four? No. Five? Yes. Let's go to the other end of the continuum. Is 97 in here? Yes. 98? No. 99? Yes. 100? No. But 100 is a yes because we're looking at the complement. The 100 goes in because it is in the universal set and not in A. Okay. And then it is also to be noted that the complement of the universal set is no solution. I mean, it's the empty set. So uh the complement of the universal set. And I always put a tail on my universal when I handwrite it. So sorry about that, but that's just what I do. Universal complement is always the empty set because the universe is all that we consider. So the complement of that, there's nothing left. All right. Okay, so let me talk briefly. I took it out. I took something out and I want to put it back in really quick because I think it makes sense for me to do so. So I'm going to have a little quick sidebar and I want to talk about subsets. I'm going to talk about the more important subset in a second, but let's just get the general gist of subsets. A subset is written, B is a subset of A if and only if every element of B is also an element of A. These can be equivalent, but don't have to be. Okay, so that's the difference here. A regular subset, just a plain old subset, can be equivalent. And so let me just give you a little example here. So let's just say if A is 1, 2, 3, 4, and B is 2, 3, 4, then we can say, and then let's say C is 2, 1, 4, 3. So let's just make a couple of statements here. We can say that B is a subset of A. We can say that B is a subset of C because 2, 3, 4 and 2, 3, 4, right? We can also say that A is a subset of C, and we could even say C is a subset of A. There's all sorts of things that we could say right there. But we're not really going to deal with just plain subsets. We're really going to hone it in and really talk about something called the proper subset. So the other kind of subset, the more useful kind of subset, says this, for all sets A and B, B is a proper subset of A, and we don't have that little extra line underneath because remember when you put a little line underneath, that could mean equal to. That's really kind of like the difference there. So it is just this sideways C, this long skinny C. So it says B is a subset of A if and only if B is a subset of A and B is not equal to A. So in other words, to be a proper subset, I love this, the cardinal number of B must be at least one element smaller than the cardinal number of A. In other words, less has to have at least one less element to be a subset. Must have at least one less element to be a proper subset. Now remember, we started all of this stuff by me telling you that notation is imperative here. Detail and notation. Detail to the reading and detail to the notation. Okay, so let's think about how many subsets can we get from a finite set? And there is actually a formula because, surprise, there's a sequence that develops from this. So let's use some problem solving skills that we have gotten thus far, um, and lean into some of the things that we learned in chapter 1 of this unit, which is some problem solving techniques and methods. And the first thing I'm going to think is I'm just going to start modeling this, right? So how many subsets can we get from a finite set? So let's list out some finite sets here. We have the empty set. We have we don't need to start with the empty set. That's just part of the gig. Sorry. So let's start off with set P. P has one element. Can we list out all the sets? List all subsets. Okay. So if a subset can be the set itself, and also every set has the possible subset of the empty set. So every set has the empty set as a subset because it's a possibility, right? So that one just gets listed every time. Now, what if we have two elements like A and B? What are all the possible subsets for there? Well, we could have itself, AB, right? We could also have just the A. We could have just the B. And we always have the empty set. All right, we might be building something. Let's write out another one. See, a B, and a C. Let's write out all the subsets here. We've got A, B, C. I always start with that one, right? Then I'm going to go for the 2-element subsets because there's only one 3-element subset. It's the same, so we're going to go A, B, A, C, B, C. Okay. Then we got our single terms. We got our A. We got our B. And we got our C. And we got our empty set. Now, we can do this again with four variables. Let's see if we can see a pattern here. So we have one element, two sets. We have two elements, four sets. Three elements, one, two, three, four, five, six, seven, eight sets. Oh, I see a pattern. I'm going to guess this is going to give us 16. And I'm going to say that T is going to give us, what would be the next one? Come on, guess it for me. Yes, 32. All right. Now, once you've seen that pattern, then we're going to take a guess. Let's guess the pattern. I think that here we have one, two, three, four, five, right? The first term, the second term, third term, right? So this is 2 to the 1 is equal to 2. 4 is equal to 2 squared. 8 is equal to 2 cubed. 16 is equal to 2 to the fourth. 32, 2 to the fifth. It looks like we've got our pattern. So I think that our pattern is going to be the number of subsets is equal to 2 to the n. And that is actually true. And we got to the end of this lecture, and I, for one, am very happy. I am hungry and I need something to drink, and we did it, and yay. And I hope you guys have a great day. And be sure to keep up. I've noticed that I've gotten quite a few lectures up, and you guys are lacking a little bit on keeping up. So that stuff's gonna come in clutch here in about a week or so when we have our first exam. You guys have a great day. See you later.